We start with a blank mode solution simulation file. Add a rectangle from the Structures drop-down menu for the substrate. Edit the rectangle. Set the X and Y spans to 16 microns. Set Z to -2 micron and the Z span to 4 micron. Under the Material tab, set the material to SiO2 glass Palic. Next, add the ring resonator from the Object Library under the Integrated Optics category. Edit the structure group. Set the position. Set LC, which is the coupling length, to 0. Set the gap distance to 0.1 micron. Set the ring radius to 3.1 micron. Set the material to Si silicon Palic. Set the base width and height, which is the width and height of the waveguides, to 0.4 and 0.18 microns respectively. Set the X span to 14 microns. And base angle to 90, which means the waveguides will not have sloped sidewalls. Using the Zoom Extent button, you can zoom the viewports around the model. Add the VAR-FDTD solver region from the Simulation drop-down menu. Edit the solver region and increase the simulation time to 5,000 femtoseconds, which is long enough for the fields to fully propagate through this resonant device. Under the Geometry tab, set the X and Y spans to 10 micron and the Z span to 1 micron. Under the Effective Index tab, we will use the default settings for the effective index method. Set the simulation bandwidth to broadband, since we are interested in the wavelength range between 1.5 to 1.6 microns, and we want to include the effect of the material and waveguide dispersion over this range. There are settings here for the broadband material fit. We will check the material fits later using the Material Explorer before running the simulation. Next, we need to select the slab mode, which is used to calculate the effective materials which are used to collapse the 3D problem to a 2D problem. The slab mode needs to be calculated for the vertical cross-section of the structure, including the core material where the bulk of the power is contained. In this case, the silicon waveguide is the core material, so we need to set the slab mode position to include the silicon. You can enter the slab mode X and Y coordinates here, but it's often easier to set the position from the graphical viewport. Click OK to close the VAR-FDTD edit window. You can see a green cross in the XY viewport which corresponds to the slab mode position. You can click and drag the green cross and move it to a position where it overlaps with the silicon waveguide. You can also see 4 blue crosses which correspond to test point locations. If I edit the VAR-FDTD solver region again, the number of test points and positions of the test points can be set from the Effective Index tab. The Material Explorer will show the calculated effective index for the slab mode as well as at each of the test point locations. The test points are only used to show the calculated effective index values at the specified positions in the Material Explorer. Their locations will not have any effect on the simulation results. On the right-hand side of the Effective Index tab, we can select the slab mode. This can either be the E mode, which is the fundamental mode where the electric field polarization is in the XY plane, the H mode, where the electric field is polarized along the Z direction, or User Select, which can be used to select higher order slab modes. We will use the E mode. You can plot the selected mode profile using the Plot Current Mode button. You can see that the fields are primarily contained in the silicon region, which is between Z equals 0 and 0.18 microns, as expected. We will use the default settings in the Mesh Settings, Boundary Conditions, and Advanced Options tabs. Click OK to accept the settings. Next, add a mode source from the Sources drop-down menu. Under the Geometry tab, set the geometry and position of the source so that it ejects from the straight waveguide at the top left of the device. Under the Frequency Wavelength tab, set the wavelength range to between 1.5 to 1.6 micron. In the General tab, we will use the default mode selection option of Fundamental Mode. Since the slab mode has been selected as the TE mode, the mode source will be injecting the fundamental TE mode. It's important to always make sure that the correct slab mode has been selected before choosing the mode to inject. Use the Plot Current Mode button to plot the field profile of the mode source along Y. The final step is to add monitors to record the transmission spectrum at the through and drop ports. Add a frequency domain field and power monitor from the Monitors drop-down menu. Edit the monitor and set the name to Drop. In the Geometry tab, set the monitor type to Linear Y and set the position and span to overlap the lower waveguide at the drop port. Under the General tab, select Override Global Monitor Settings and set the number of frequency points to 500 and click OK. With the drop monitor selected, click the Duplicate button on the left-hand side toolbar to duplicate the monitor. Edit the monitor and set the name to Through. Under the Geometry tab, set the X position to 4.2 micron and Y to 3.6 microns. Add a frequency domain profile monitor from the Monitors drop-down menu. Set the name to Profile. Set the X and Y spans to 10 microns and Z to 0. In the General tab, override the Global Monitor settings and set the number of frequency points to 100. Now the simulation has been set up, and in the next unit we will run the simulation and collect the results.